Welcome back to the Deep Dive. We're peeling back another layer today, venturing into a chapter that feels, well, less like a textbook and maybe more like a thrilling scientific treasure hunt.
That's a great way to put it. We're diving into Chapter 5 of Outlive by Peter Attia. It's titled Eat Less, Live Longer, The Science of Hunger and Health.
And our mission, as always, is to help you make sense of it all. We're going to unpack the key ideas here, trace this really surprising story of discovery, and connect the dots between what we eat, how we age, and, well, a fascinating molecule.
Right. And the author kicks things off not in some high-tech lab, but on a really remote island.
Okay. Tell us about that.
It starts with a trip the author took back in 2016. He went to Easter Island, Rapa Nui, with a few friends, including two pretty prominent scientists, David Sabatini and Navdeep Chandel, and also Tim Ferriss was there.
Easter Island. Wow. That is isolation.
Exactly. Think about it. This tiny speck of land, 63 square miles, and it's over 1,000 miles from the nearest significant human settlement. Just ancient volcanic rock, sheer cliffs dropping into the ocean.
Known for the giant statues, the moai mostly. But they weren't there just for sightseeing, were they?
No, not primarily. They were on a kind of scientific pilgrimage, you could say.
A pilgrimage. To see what?
They were visiting the birthplace of a molecule that had already, transformed medicine and maybe even more astonishingly shown this ability to extend maximum lifespan in mammals. Right. And there's even this local legend, interestingly, about the Ranokau volcano crater having, healing powers, which actually ties right into the scientific story here.
Okay, I'm intrigued. So how does a major scientific breakthrough come from, dirt on a tiny island?
Well, it goes way back. Back to 1964, a Canadian expedition collected soil samples from that exact crater area you mentioned.
Okay.
And one of those samples eventually ended up back in Montreal at a pharmaceutical company called Ayerst.
Right. And someone there had to sift through these samples.
Exactly. A dedicated biochemist, Suren Segal. He was tasked with screening these things, looking for novel compounds, and in that specific Easter Island soil sample, he found something, a really potent antifungal agent.
An antifungal?
Yeah, produced by a bacterium called Streptomyces hygroscopicus.
So, for athlete's foot. I think the source mentioned something about that.
Yeah, it does. Apparently, Segal initially thought, hey, maybe this could cure athlete's foot. His son even remembers him mixing up a batch for a neighbor who had some kind of rash, and well, it cleared right up.
That's amazing.
But its real significance, as it turned out, was much, much bigger than that.
Okay, but before they got to that bigger discovery, wasn't there a kind of dramatic twist? Didn't the company shut down his lab?
That's the incredible part of the story, yes.
Right.
Ayers closed the Montreal facility and the order came down. Destroy all your research compounds. Standard procedure, maybe, but devastating. But Segal, he just couldn't do it. He knew he was onto something potentially really important, so he smuggled a jar of the active substance home.
No way.
Yes. His family literally kept it in their freezer. Apparently, it was labeled, "Do not eat."
Do not eat. I love that. So this potential breakthrough is just sitting there next to the frozen vegetables.
Pretty much. Until 1987, when Wyeth acquired Ayerst, Segal had moved to their labs in New Jersey by then. And when someone asked about interesting past projects, he was like, well, I have this, and produced the sample from his freezer.
And the research was back on.
The research resumed, yeah. And they moved pretty quickly beyond just thinking about rashes.
So what did they find then? What was the big deal?
They discovered its really profound effects on the immune system. That was the major breakthrough.
Ah, okay.
And that led to its FDA approval in 1999 for preventing organ rejection in transplant patients. The author himself actually used it a lot when he was surgical resident. You might also know it by the name sirolimus.
Sirolimus, right. And it's used for other things, too, not just transplants.
That's right. It's used as a coating on arterial stents, to help prevent arteries from reclogging after procedures.
Okay.
And a related molecule, an analog called everolimus, was approved for a type of kidney cancer back in 2007. So it's already a molecule with significant medical impact.
Definitely.
Though, just as a little side note, the source mentions that the commemorative plaque they put on Easter Island about the discovery, it got stolen.
You're kidding. Even the plaque has drama.
Right. But the key thing Segal noted way back, the property that really pointed towards its, let's say, even broader significance for biology, was that it slowed down cellular growth and division.
That observation seems critical.
It was. And scientists like David Sabatini, one of the guys on that Easter Island trip later on, they really picked up on that thread. Sabatini's work, among others, helped figure out exactly how rapamycin was doing this.
How it worked at the cellular level.
Yeah. It targets a specific protein complex inside our cells.
The one named after it, MTOR.
Exactly. Mechanistic target of rapamycin. MTOR. And listen, this isn't just some random cellular part. What makes MTOR so incredibly interesting, so important, is that it's a major mediator of longevity.
Okay.
And it's what scientists call highly conserved.
Highly conserved, meaning it's basically everywhere in all sorts of life.
Pretty much, yeah. It's found in virtually all life forms we know of, from single-celled yeast to worms, flies, mice, all the way to us humans.
That implies it's really fundamental. Evolution kept it for a reason.
A very good reason. It's absolutely fundamental to life. And rapamycin, this molecule from a bacterium found in dirt on a remote island, just happens to inhibit this ancient, super important pathway.
It's almost like finding a key to this ancient biological lock.
That's a really good analogy. The source compares MTOR to the cell's general contractor.
Okay, general contractor. How so?
Well, its main job is sort of balancing the cell's need to build and grow, reproduce against the availability of materials, which are nutrients.
So if there are lots of nutrients around, the contractor gets the green light to build.
Spot on. Nutrients plentiful. MTOR is active. The cell gets the signal. Grow, divide, make new proteins, prepare for reproduction. It's go time.
And the flip side, when nutrients are scarce.
Then the opposite happens. If nutrients are low, MTOR gets suppressed, turned down. The cell shifts gears. It goes into, conservation mode, cleanup mode.
Slows down the building.
Right. Growth slows or stops. It starts breaking down old components to reuse the parts. It conserves energy. MTOR is basically sensing nutrients, especially amino acids, and telling the cell how to manage its resources.
Okay, and this connection between MTOR and nutrient sensing is where we get to that huge discovery that really put rapamycin on the map for aging research.
You're thinking of that big 2009 study, the one that prompted headlines like that New York Times one? Antibiotic delayed aging in experiments with mice.
Yeah, although the author points out it was kind of buried inside the paper, like page A20 or something. But the actual study published in Nature was incredible. What exactly did it show?
It showed that giving rapamycin to mice significantly extended their average lifespan. About 13% longer for females, 9% for males, which is already impressive.
That is impressive. But there was more, right?
Yes. Here's the really stunning part. They started giving the drug to the mice when they were already old, like the mouse equivalent of maybe a 60-year-old human.
And giving it that late in life still worked.
It worked dramatically. It boosted their remaining life expectancy by a huge amount. 28% longer for males and an amazing 38% longer for females.
38%.
Yeah. The source uses the example. Think about what that would mean for a 60-year-old woman, potentially living to 95 instead of, say, her early 80s. It was just wow.
And this was the first time any molecule had done that, extended maximum lifespan in a mammal.
The very first. And critically, the study itself was super rigorous, which, is really important in the aging field. Sometimes things get overhyped.
Right, you hear about lots of things.
Exactly. But this wasn't just one lab getting a lucky result. It was done by 3 independent labs, 3 different teams. They used almost 2,000 mice, different genetic backgrounds, and the results were consistent. Reproducible.
That's the gold standard in science, isn't it? Reproducibility.
It really is, and it stands in stark contrast to some other things that got a lot of press, like resveratrol or NR. Those didn't really hold up when subjected to the same kind of rigorous multi-center lifespan testing in mice.
So the rapamycin mouse data was solid. It strongly suggested there's something good, as the source puts it, about turning down MTOR, at least temporarily.
Which really flagged rapamycin as having serious potential as a genuine longevity drug. And, for scientists studying aging, while the molecule was new, the underlying concept wasn't entirely out of the blue.
How so?
It connected beautifully to this idea that's actually been floating around for centuries.
You mean the idea that just eating less might make you live longer?
Exactly that. People have noticed connections between diet and lifespan for ages. Hippocrates touched on it. But the first person to really document putting this into serious, rigorous practice wasn't a scientist.
Right. It was that Italian guy from the 16th century, Elvis Cornaro.
That's him, a wealthy Venetian nobleman. Apparently enjoyed his food and drink, maybe a bit too much. By his 40s, his health was a mess.
What kind of problems?
The source describes this train of infirmities: chronic pain, gout, stomach issues, constant thirst, weight gain. Sounds a lot like, well, early signs of diabetes or metabolic syndrome. His doctors basically told him he needed to drastically change his ways, or else.
Which must have been hard advice to take for a nobleman used to feasting.
Oh, absolutely. He was reluctant. But apparently his health got so bad, he finally decided to try this extreme approach, what he called a Spartan diet.
And Spartan is right. It was severe restriction, wasn't it?
It really was. Something like only 12 ounces of food per day, often just simple stuff like bread, egg yolk, maybe some broth or stew, plus 2 small glasses of wine.
12 ounces. That's tiny.
It is. And he specifically wrote that he always left the table with a disposition to eat and drink still more. He never felt full. He was always a little bit hungry.
Wow. And did this drastic change actually work for him?
Incredibly well. Within about a year, he reported feeling completely transformed, his pains gone, full of energy. He felt entirely freed from all my complaints.
Amazing.
And he stuck with it. He lived well into his 80s, maybe even older. Accounts vary. He was so convinced this was the secret to health and longevity that he wrote a book about it, Discourses on the Sober Life.
And that book became a big deal.
Hugely influential, praised by people like Benjamin Franklin, Thomas Edison. You could maybe call it one of the very first best-selling diet books ever.
So Cornero's personal experiment centuries ago kind of set the stage for modern science to investigate this more formally.
Absolutely. His experience and others like it eventually led scientists in the mid-20th century to start rigorously testing this idea in lab animals, which is where we get the field of caloric restriction research, or CR.
Okay, and let's be clear about what CR means in the lab. It's not just starving the animals, right?
No, definitely not. It's very specific. It means feeding the animals significantly fewer calories, typically like 25–30% less than their control group counterparts who eat as much as they want. But, and this is crucial, they still get all the essential vitamins, minerals, proteins, all necessary nutrients. It's caloric restriction without malnutrition.
Got it. And when scientists did this, what did they find?
The results were remarkably consistent across an incredible range of species.
Like what?
Well, CR was shown to lengthen lifespan, often by a lot, like 15% to 45%, in yeast, worms, flies, fish, rats, mice, hamsters, spiders, even dogs, pretty much everything they tested it on.
Except?
The weird exception seems to be houseflies for some reason, but otherwise it was almost universal.
And it wasn't just about living longer, right?
Yeah.
They were healthier too.
Exactly. That's a key point.
Right.
The calorie-restricted animals weren't just living longer. They were markedly healthier for their age. They developed fewer spontaneous cancers. Their organs looked younger. It improved their health span, not just their lifespan. And there was often a dose-response effect. The less they fed the animals, within limits, the longer they lived.
Okay, so the animal data for CR is incredibly strong and consistent. Why isn't severe, lifelong CR the go-to recommendation for human longevity then?
Yeah, that's a really important question, and the source addresses it directly. While the lab results are compelling, translating that specific protocol severe, lifelong CR to humans living complex lives in variable environments is problematic.
What are the main issues?
Well, first, the controlled lab setting protects animals from things like infection or cold, where being extremely lean might actually be a disadvantage in the real world. Second, just practically speaking, sustaining that level of restriction, like Cornaro did, feeling hungry all the time for decades. That's incredibly difficult for most people, psychologically and socially.
Yeah, I can imagine.
And third, there's actually no clear evidence that such extreme CR maximizes longevity in humans, given our complexity and environment. The potential gains might be wiped out by increased risks from infections, accidents due to frailty, that sort of thing.
So the takeaway isn't necessarily to adopt the extreme CR protocol itself.
Right. For most people, that's probably not the best strategy. But the real value of all that CR research was immense. It wasn't about the diet plan per se. It was about what it taught us about the biology of aging.
It helped uncover the underlying mechanisms.
Exactly. By studying why CR worked, scientists discovered these fundamental cellular pathways related to nutrient sensing, stress resistance, and metabolic efficiency. And guess what? They all connect back to MTR.
Okay, so CR works, at least partly, by affecting MTR. And you mentioned another player involved here too, AMPK.
Yes, AMPK. AMP, activated protein kinase. If MTR is the general contractor responding to abundance, you can think of AMPK as the cell's low fuel light or its energy sensor.
So AMPK turns on when energy is low.
Precisely. It gets activated when nutrient levels drop, or during things like exercise, basically, anytime the cell's energy charge is running low.
And what does AMPK do when it gets activated? What's its job?
Its job is to help the cell conserve energy and find alternative fuel sources. It tells the cell, hey, resources are scarce, let's tighten our belts and find more fuel.
How does it do that?
One major thing it does is stimulate mitochondrial biogenesis.
Making new mitochondria, the cell's power plants.
Exactly. It helps create new, efficient mitochondria and clear out old, damaged ones. It also helps mobilize fuel reserves, telling the liver to release glucose, telling fat cells to release fatty acids for energy.
And how does AMPK connect back to mTOR, the growth pathway?
Here's the crucial link. AMPK actively inhibits mTOR activity.
Okay, so low energy activates AMPK.
Which then helps put the brakes on mTOR. It makes sense, right? If energy is low, you don't want to be investing heavily in growth and division. A drop in amino acids, specifically, seems to be a really potent signal to shut down mTOR and those anabolic or building processes.
Right. And when mTOR is inhibited, when growth is shut down, the cell shifts into that cleanup mode you mentioned earlier. Autophagy.
Yes, autophagy, which literally translates to self-eating or self-devouring. It sounds dramatic, but it's a vital housekeeping process.
The cell's recycling program.
That's a perfect way to think about it. When MTR is low, autophagy ramps up. Specialized parts of the cell, called lysosomes, basically engulf and break down old, damaged, or unnecessary proteins, worn-out organelles, cellular junk.
Why is that so important?
It's like taking out the garbage and recycling the useful bits. It clears out debris, gets rid of misfolded proteins, or aggregates the kind of stuff linked to neurodegenerative diseases like Parkinson's, Alzheimer's, ALS. It even clears pathogens. It keeps the cell clean, efficient, and more resilient to stress.
And this process, like maybe other repair processes, tends to decline as we age.
It does seem to become less efficient with age, yes. And impaired autophagy is linked to a lot of age-related problems. But here's the key connection for our story. Autophagy is triggered by the same things that suppress mTOR. Things like temporary nutrient reduction fasting, exercise.
And the drug rapamycin.
Exactly. Rapamycin, by inhibiting mTOR, directly promotes autophagy. This process is so fundamental to cellular health that the research uncovering its genetic control won the Nobel Prize in Medicine in 2016.
Okay, so let's recap. We have this molecule, rapamycin, found in Easter Island dirt. It inhibits mTOR, a key regulator of growth linked to nutrient sensing. Inhibiting mTOR seems to promote longevity, at least in mice, possibly via mechanisms like activating autophagy, this cellular cleanup process. The potential for human health seems huge.
It does. Researchers like Matt Kaberlein, who we've mentioned, are really optimistic about its potential to extend not just lifespan, but health span, the period of healthy life in humans. But there have been significant hurdles.
And the biggest hurdle has been the side effect profile, particularly the immunosuppression risk.
That's been the major concern, yes. Remember, rapamycin got its start as an immunosuppressant for transplant patients. It was approved and used at doses and schedules designed to suppress the immune system continuously, indefinitely, to prevent organ rejection.
Which is essential in that context.
Absolutely critical. But the idea of giving a drug known to suppress immunity to healthy people just to slow aging, that raised major red flags about increasing their risk of infections or maybe even cancer. It seemed like a non-starter for a long time.
But then came that study you mentioned earlier, the one that kind of challenged that whole paradigm.
Exactly.
Yeah.
That 2014 study, led by Joan Manick and colleagues, using the rapamycin analog everolimus in older but generally healthy adults, it was pivotal.
What was so surprising about it?
They gave a moderate dose, but crucially only once a week instead of daily like in transplant patients. And the results were stunning. Instead of suppressing the immune system, this weekly dose actually enhanced the participants' adaptive immune response to a flu vaccine, and it did so with fewer side effects than expected.
Wow. So less frequent dosing actually boosted immunity.
It suggested rapamycin isn't just a blunt immunosuppressant. It might be more of an immune modulator. And the effect really depends on how you dose it.
How does that work? Why would dosing frequency change the effect so dramatically?
Well, the thinking relates to those two mTOR complexes we touched on briefly, mTORC1 and mTORC2. The longevity benefits seem primarily linked to inhibiting mTORC1. The traditional high-dose daily regimen used for transplants likely inhibits both mTORC1 and mTORC2 pretty heavily, leading to the significant immune suppression.
Okay.
But the hypothesis is that this cyclical, less frequent, lower-dose regimen, like in the 2014 study, might preferentially inhibit mTORC1. This could potentially give you the desired longevity and autophagy benefits while having less impact on mTORC2 and therefore less unwanted immune suppression. Ideally, you would want a drug that only hits mTORC1, but we don't have that yet.
So this nuanced understanding of dosing helps, but getting rapamycin approved specifically for, slowing aging in healthy people is still a massive regulatory challenge, isn't it?
Oh, absolutely. It's a huge hurdle. Even if side effects are reduced with intermittent dosing, regulatory agencies have a very low tolerance for side effects when considering a drug for prevention in otherwise healthy individuals.
It doesn't fit the usual mold.
Exactly. The source frames it as a mismatch between our current medical framework, Medicine 2.0, which is focused on treating established diseases, and the goal here, which is more like Medicine 3.0, preventing disease by targeting the aging process itself. Slowing aging or delaying the onset of age-related diseases aren't currently recognized as standard drug approval endpoints.
But the argument from the source is that maybe they should be, right? Given that aging underlies the diseases that kill most people.
Precisely. If aging drives the diseases that kill 80% of us, heart disease, cancer, neurodegeneration, diabetes, then targeting aging itself could be the most powerful preventive medicine imaginable. And that, the author argues, warrants a serious conversation about what level of risk is acceptable for such a potentially huge benefit.
Are there any signs that regulatory thinking might be shifting on this?
There are encouraging signs. A really significant one is the FDA giving the green light to the TAME trial. That's targeting aging with metformin.
Metformin, the diabetes drug.
Right. It's an old, widely used diabetes drug. Some observational studies suggested it might have longevity benefits. Diabetics taking it seem to have lower cancer rates, and in some studies, maybe even lived longer than non-diabetics without the drug. Though it's important to stress, that's correlation, not proof, which is why the TAME trial is needed.
And what's groundbreaking about the TAME trial is its endpoint, right?
Exactly. It's not looking at just one disease. Its primary endpoint is the delayed onset of a composite of major age-related diseases, things like heart attack, stroke, cancer, dementia, heart failure. It's using this cluster of diseases as a proxy for measuring an effect on the underlying aging process.
It's a big step.
It's a huge conceptual step for the field and for regulators. The author of the source expresses hope that a similar large-scale human trial could eventually be done for rapamycin, which he believes might have even greater potential than metformin.
So while we wait maybe years for large human trials on rapamycin for aging, there's other really interesting research happening now, isn't there, in dogs?
Yes, the Dog Aging Project, led by Matt Kaberlein again. This is a major clinical trial testing rapamycin in companion dogs, pets living in people's homes.
Why dogs?
They're actually a fantastic model for studying aging relevant to humans. They're large mammals. They share our environment very closely. They eat similar foods in some cases. And crucially, they develop many of the same age-related diseases we do, cancer, heart disease, cognitive decline, just on a much faster timescale. What takes decades in us might take only years in a dog.
So studying them could give us clues much faster. What are they finding so far?
The preliminary findings from earlier phases have been really promising. They've seen indications that rapamycin improved heart function in older dogs. It seemed to have a kind of rejuvenating effect on certain organ functions.
Rejuvenating, wow.
Yeah. They've also observed things like reduced systemic inflammation, maybe through effects on senescent zombie cells, potentially improved cancer surveillance by the immune system, and even signs of better periodontal or gum health.
That's quite a range of potential benefits.
It is. The main phase of the trial is underway now, with around 600 dogs enrolled. They're using that intermittent weekly dosing strategy. Results are expected around 2026.
And if those results are positive, what would that mean?
Well, the source suggests that strong positive results showing clear health span benefits and good safety in dogs could really accelerate the conversation around using rapamycin for longevity in humans. It might make off-label use more common, or potentially pave the way for more focused human trials.
And the author mentions that some people are already using it off-label now.
Yes. He notes that a growing number of people, including himself and some of his patients, are taking rapamycin off-label with the goal of geroprotection, finding that the cyclical dosing seems to largely mitigate those unwanted side effects in their experience. Of course, that's anecdotal, not controlled trial data yet for healthy humans.
Okay, so pulling all these threads together then, from this whole deep dive into Chapter 5, we've gone from Easter Island soil to MTOR to caloric restriction, AMPK, autophagy, mouse studies, human trials, dog trials. What's the big picture, the main takeaway?
I think it all converges on one really powerful central idea.
Yeah.
What we eat, when we eat, the simple availability of nutrients, and how our bodies sense and respond to that, basically. Our metabolism seems to play an absolutely fundamental, maybe even an outsized role in determining how long we live and how healthy we remain as we age.
It really is fascinating how this molecule found in remote dirt and these ancient observations about simply eating less all point towards the same core biological machinery regulating aging.
It is quite remarkable. It underscores just how deeply wired this connection between metabolism and aging is in our biology, conserved over vast evolutionary time.
Absolutely. And exploring this connection, understanding MTOR and these related pathways, really sets the stage for figuring out, well, what happens when things go wrong metabolically?
Which leads us right into the next critical piece of the puzzle.
Right. If this link between metabolism and aging is so profound, so ancient, it really makes you think, how does our modern diet, with its constant abundance, its specific types of nutrients, how does that actually challenge these ancient biological systems we've just been talking about? It's quite a thought to chew on, isn't it?
It really is a crucial question for our time.
Indeed. And that, funnily enough, is exactly where the next chapter of the book goes. It takes a much closer look at how metabolic dysfunction, metabolic disorders, specifically act as a primary driver, really instigating and promoting the chronic diseases of aging, building directly on this foundation we've laid today.
Yeah, looking forward to getting into that. It connects all these dots to the diseases we actually face.
We definitely are too. So thank you for joining us for this deep dive into Chapter 5.
Stay tuned for more as we continue unpacking this fascinating material together.